Today we are going to see the vector product of two vectors. And this is the definition 110 of vector product. Recalling the slight incompleteness we initially had with the definition of scalar product, namely when the vectors can be 0, so we deal with those cases in the beginning itself here. So we start like this, let A and B be any two vectors. If A is the 0 vector or B is the 0 vector, or of course if both are 0, or means inclusive or, then we define the vector product A times B, or you can say A cross B of A and B to just be the 0 vector. Note carefully that here the result is a vector. Although it's 0, but it's defined to be a vector. Next we have the case where neither A nor B is the 0 vector. Both of them are non-zero vectors. Then they will have geometric representations as OA and OB, geometric vectors, which are directed line segments of positive length. This time none of them is a single point because the original vectors are non-zero vectors. And that is why we can talk about angle between the line segments OA and OB because they have some lengths. And let theta be the angle between OA and OB such that theta lies between 0 and pi radian. Let n hat be the unit vector perpendicular to the plane OAP such that these vectors A, B and n hat, when considered in that order, form a right-handed set. To the plane OAB means the 3 points OA and B, wherever they are, they will determine a plane. N hat is a unit vector perpendicular to the plane. So if the plane is like this, n hat may be pointing in this direction or it may be pointing in that direction. So there is an ambiguity. However, the ambiguity is gone once you specify this also, that A, B and n hat, when considered in that order, they have to form a right-handed set of vectors. Then the vector product A times B again, in this case also, of A and B is defined by this equation. A times B equals the magnitude of A times the magnitude of B times sine theta times that unit vector n hat. So note one thing, that here you are having sine theta, whereas in the definition of scalar product of two non-zero vectors you have cos theta. So that is one difference. Another difference comes from this n hat. This is a vector. The result of the scalar product of two vectors is a scalar, but the result of the vector product of two vectors is a vector. In this case also and in the previous case also, where at least one of the vectors is the 0 vector. And there is one more thing. Do you see this requirement that this set needs to be right-handed? And when you talk about handedness of a set of vectors, the order in which you take the vectors matters. If you change the order, say in place of A you write B, and you switch them, then this n hat will no longer work. The other n hat has to be chosen. Other n hat means the other unit vector which points opposite to this one. Okay, that has to be chosen to maintain right-handedness. So essentially what that means is that in place of A cross B or A times B, if you consider B times A, then the result is no longer this. Okay, in spite of theta being theta and the magnitudes of A and B being the same, this changes, so the result also changes. That means, unlike the normal operations that we are so familiar with, for example, multiplication of two real numbers which are commutative, vector product is not commutative. To better understand what's going on, let's look at this diagram. You can see here the representation OA of the vector A, the representation OB of B, the angle theta between them which lies between 0 and pi radian, and one dashed line also. And you should understand, probably you already know, that this diagram is not supposed to mean that these lines are lying on this whiteboard. No. This OA and OB are lying in a plane, say a horizontal plane like this. And this dashed line is perpendicular to this plane in that sense. And to indicate that this is perpendicular to both OA and OB, we have drawn these rectangles of so small rectangle just to show that it is perpendicular. Alright. Now what is the requirement? The requirement is that this set be right-handed. What does that mean? You recall that this means that as you take your right hand, say this is, let me just grab two things. This is say OA and this is OB. As I take my right hand and curl my fingers, except the thumb, I curl the other fingers in such a way that I rotate from A to B. Then my thumb points upwards. So that is the direction in which n hat is pointing. If that happens, if this is maintained, then this becomes a right-handed system. So then by the definition, what is A times B? A times B is that vector whose magnitude is magnitude of A times magnitude of B times sin theta, and whose direction is n hat. But let's be absolutely clear about everything. Magnitude by definition is either 0 or positive. Is it possible for this part to be negative? Obviously, the magnitudes of A and B are not negative. In fact, in this case where A and B are both non-zero, you don't have that condition here, but A and B are both non-zero, that means this is a positive real number, this is a positive real number. What about sin theta? Sin theta is not always positive, sometimes it is negative also. But you go back and see the restrictions on theta. Theta lies between 0 and pi radian. In that range, or in that part of the domain for the sine function, sine is actually positive, means it's non-negative. So that is why this really is the magnitude of A times B. That is the magnitude, and this is the direction in which the vector A times B is pointing. Its direction is the same as the direction of this n hat. Alright, and what did I say just now? That if we change the order, then things change. Say instead of considering A times B, you consider B times A. Then by definition, you have to change this set as well. You have to write B here and A here, followed by n hat, but that n hat actually won't really be this n hat. You have to still use your right hand. Still this is your OA and this is OB, but this time you need to come from B towards A, and you are forced to then move your right hand like this and then curl your finger. So then you are coming from there to this one. This time, however, my thumb is pointing downwards. So that should be the direction of n hat. That's another n hat to maintain right-handedness. So changing the order changes the result. Okay, that's another vector. Another means you do not even have to consider this magnitude part. It's pointing in this direction. That one B times A is pointing in the opposite direction. So they are not the same. Just like we have laws of algebra for scalar product, we have laws for the vector product as well. The first one says that B times A equals minus of A times B, the thing that I was talking about here just now. One can express this by saying that this is anti-commutative. Vector product is anti-commutative. It's not commutative, but specifically because of this thing, it's called anti-commutative. The second one is distributive law, which is exactly like what we have also for the scalar product. There we had A dot B plus C equals A dot B plus A dot C. Here we have A cross B plus C equals A cross B plus A cross C, or A times C. And the third one is a kind of associative law involving scalar multiplication and vector product. Here you understand that this lambda is a scalar. Lambda A times B or lambda A cross B equals lambda times A cross B. We won't really be concerned about proving these things. Instead, we will use them whenever we need. You can find proofs of these things in any vector algebra book, or you can apply the definition and prove them yourself. They are not really that difficult. And besides these laws, we also have properties for vector product. The first one says that the vector product of a vector with itself is the zero vector. Actually, you can see it instantly. If the vector A is 0, then by definition this vector product is 0 vector. And if A is non-zero, then you apply the definition of vector product to A times A. You just consider the angle between A and A. Between A and A means A is an abstract vector, so angle between A and A really does not make much sense, but you consider some representation of A, which is a geometric vector. So there you can think of the angle between that representation and itself, which is 0 radian, or in degrees 0 degree, and sine 0 is 0 whether you are measuring in radian or degree. So that's how you get 0 vector in that case as well. The second one, this also follows immediately from the definition, says that the vector product of two vectors is 0 in any order if and only if either the vectors are 0, either one of them is 0 or both are 0, or they are both non-zero and they are parallel. In that case also we are going to get 0 vector. And then we have this third one, if I hat, j hat and k hat form a standard basis. Let's recall that a standard basis is an orthonormal set of vectors. That means the vectors are unit vectors and they are mutually orthogonal, perpendicular to each other, and they form a right-handed set. If so, then we have the following. I cross j is k, j cross k is I, and k cross I is j. You think of these vectors along the x, y and z axis of a rectangular three-dimensional coordinate system in such a way that you have a right-handed set and apply the definition of cross product or vector product, you will instantly get that I cross j is k and the others are these things. And these other cross products are 0 or vector products are 0, that follows from this one directly. And this is the fourth one. Say we have two vectors a1 and a2. Each one has been expressed as a linear combination of standard basis vectors I hat, j hat and k hat. Like this, lambda 1 I hat plus mu1 j hat plus mu1 k hat. That is a1. And for a2 it is lambda 2 I hat plus mu2 j hat plus mu2 k hat. Then the vector product of a1 and a2 is given by this determinant, where the first row consists of these standard basis vectors, the second row consists of the scalars or coefficients of a1 in that order, okay, in the same order as I, j and k, and the third row consists of the coefficients of a2. Now this is only a memory aid, okay. I need to now write down what this really means. This is what it means, this vector, which you get if you expand this determinant with respect to the first row, forgetting that this I, j and k are vectors, not real numbers. You treat them as if they are real numbers and expand the determinant. This is what you get. For I hat you are going to get mu1 mu2 minus mu2 mu1 minus. So you are just applying the rule for expanding a 3 by 3 determinant above the first row. Minus, for j hat you are going to get lambda 1 mu2 minus lambda 2 mu1. Then it becomes plus Then for k hat you remove the column and row containing k hat and consider the remaining things. So that way you get lambda 1 mu 2 minus lambda 2 mu 1. This is only a memory aid in the sense that its meaning is actually it is not a determinant in the ordinary sense, but because this follows this pattern and it's difficult to remember this, whereas it's much easier to remember this that we write this like this. That's all. And finally, let's consider one example. Example 1.8. Two vectors are given. A is this vector 2i minus j plus 2k and b is the vector minus I minus 3k. We have to find a unit vector perpendicular to both a and b. But before we solve this example, let's go back to the fourth property. How will you prove this? Well, to prove this, you first write what a1 and a2 are, okay, because each one of them is a linear combination of standard basis vectors ij and k, so you write them. So you have their vector product, and then you apply the laws of algebra for vector product to expand that, I mean to carry out that product, and then from that you will get this. Now let's solve this one. Because our vectors a and b are both non-zero vectors, so by definition of vector product, their vector product will be perpendicular to both a and b. So that way we can proceed. So let us first calculate the vector product of a and b, which by property 4 is this. So here in the first row you have I hat, j hat and k hat. In the second row you have the coefficients of a, 2, minus 1 and 2. Actually you can also say the components of a in the directions of I hat, j hat and k hat, because keep in mind that these are orthonormal vectors. You go to the previous video and see what we said there. But anyway, so here we have 2, minus 1 and 2. And in the third row we have the coefficients or components of b, minus 1, 0 and minus 3. Note carefully that we do have j hat here but with coefficient 0. Now we need to calculate what this is. I of course leave the details to you. I mean it's just a simple expansion. This is what you will get, 3i plus 4j minus k. So that means we have got a vector which is, this vector which is perpendicular to both a and b. But that's not exactly what we want. We want a unit vector. And to have a unit vector, the power is gone. Anyway, and to have a unit vector, we have to then divide this vector by its magnitude. So that means we need to calculate the magnitude. So if we calculate the magnitude like this, then we get square root of 26. What exactly did we do here? We applied the first, you go back and see the first property of scalar product. Do you remember? The square of the magnitude of a vector is the scalar product of that vector with itself. Our vector now is a times b, vector product. So the square of its magnitude is this times itself, which you know how to calculate from our previous videos. 3 square plus 4 square plus minus 1 square. This is 26 and that's how the magnitude is square root of 26. It won't be minus root 26 because this is by definition non-negative. So the required unit vector is either this or this. This one you obtain by just simply dividing a times b or a vector product b by its own magnitude, that is square root of 26, and the other one is its negative. These are the two possibilities. And with that, let me end this video here itself. Next week we are going to see triple product of vectors. There are two types of triple products. Triple products because three vectors will be involved, unlike these ones where two vectors are involved. Scalar triple product and vector triple product.